Welcome you all to a new session. In this session we are going to see about sequential circuits. Sequential circuit means the circuit which is having a feedback network. Now till now we were seeing all the combination circuits. Those were the circuits which were having only inputs and outputs. There was no feedback element which was present under combination circuits. And from this session onwards we are going to deal with sequential circuits, and the sequential circuits are the circuits which are having feedback network. In that feedback network, let's see what are the elements or what are the circuits which comes under sequential circuits. Sequential circuits, generally the sequential circuits got input, output as well as output, and this output is to be stored under using a memory element, and that memory element, through that memory element again I am going to provide that stored a value along with my input as a value to my sequential circuit. So the circuit which is framing with the help of this kind of combinations, we call it as sequential circuits. What are sequential circuits? Like what are the examples of sequential circuits? Like we have latches, flip-flops, registers and something. Those are extension versions of our flip-flops only. And latches and flip-flops are basically, these are called as 1-bit storage elements. 1-bit storage element. Now latches are of, again you can see the latches which are there currently are SR latch, D latch. Now coming to flip-flops, we have SR flip-flop, D flip-flop, JK flip-flop, and the last one is T flip-flop. So latches are two types, SR latch and D latch. Flip-flops are four types, SR flip-flop, D flip-flop, JK flip-flop and T flip-flop. Now everything is a 1-bit storage elements. Now what a difference makes latches and flip-flops is, latches are level triggered, means it is going to trigger at only levels. Now this is, if this is a wave, this is going to get on at only this particular. Now if it is triggered at this particular level, that is called as positive edge, positive level triggered latch. If it is triggered at this particular edge, then it is called as negative level triggered latch. Whereas flip-flops are edge triggered elements. Edge means it should get on at this particular point, it should get off at this particular point, on at this point, off at this point. Means at edges only my circuit is going to get on or off. On or off, those kind of situations will take place for flip-flops. So flip-flops are edge triggered elements, latches are level triggered elements. Now in this session we are going to see about SR flip-flop and D flip-flop. Let us see SR flip-flop. SR flip-flop. Now SR flip-flop is constructed using 4 NAND gates. Now you can see this is a NAND gate connected to one more NAND gate which is having S as input, and I am having one more NAND gate connected to one more NAND gate. This is crossly connected to this one. This is cross coupled. One output is Q, the other output is Q bar. Here the input is R. A clock is provided to this. So this is the circuit diagram for my SR flip-flop. Now what is the next thing, like how the transitions are happening under SR flip-flop? Let's see transition table. Transition table means for what inputs my circuit is going to behave, its outputs, how the outputs are changing for my output. So 0, 0, two input variables are there, so I am having 4 combinations. So 0, 0, 0, 1, 1, 0, 1, 1. For 0, 0 it is no change, means my output will not change for 0, 0. Next, for 0, 1 combination. For 0, 1 combination it is reset state, means my circuit is getting resetted for 0, 1 combination. For 1, 0 it is called as set state, means it is going to be in a set mode. Reset means value is 0, set as value is 1. Now for 1, 1 it is called as undetermined state, means I am not going to have a perfect determined value for 1, 1 state. So this is the transition table for my SR flip-flop. Let's get into the next thing, that is characteristic table. Now you know the transition table of a given SR flip-flop. Let's see the characteristic table. Characteristic table means my present state can be either 0 or my present state can be either 1. So my characteristic table, let us draw the characteristic table. Characteristic table means I am going to define what exactly the behavior of my SR flip-flop. So SR is my input values. So for SR values, my present state, that is Qn, and my next state will be Qn plus 1. So let's define them. So for 0 0 combination, my present state can be 0 value or my present state can be 1 value. So this is 1. For 0 1 state, my present state can be 0 or 1. For 1 0 combination, my present state can be either 0 or 1. For 1 1 combination, my present state can be either 0 or 1. Right? Now, for SR 0 0, my output function was no change. Means whatever my present state will be, that the same will be the next state representation for my SR flip-flop. For 1, it is going to be 1, same as it is, means no change. This is a combination which is telling me no change, that is I am not going to change any state value for my 0 0 input combination. Whereas for 0 1 state, my output function was reset, that is 0 state, means irrespective of my present state, my output is always 0. So this is reset. Next, for 1 0 combination, irrespective of my present state, my next state is always 1, that is a set state. This is set state. And for 1 1 combination, irrespective of my present state, my next state is always undetermined, means I don't know what value is getting generator here. So this is undetermined. So for this is the characteristic. Previous thing was transition table. Now this is characteristic table. These are the values how we define. This is my present state. This is my next state. How the next state is getting generated? Now for a circuit, for a sequential circuit, I am providing input. I am getting a output. Right? So this output we are storing under a memory element. Right? And again this value I am feeding along with my input plus stored value. So input plus stored value is giving me next state. This stored value is my present state. So present state along with my input is going to generate next state. Only generated output is present state. So input plus present state gives me next state. So that is what Qn is my present state, Qn plus 1 is my next state. Coming to my the next thing, that is excitation table. Excitation table for my flip-flop. Here we observed using inputs and present state we got next state. But here we need to observe next state, that is Q and Qn plus 1. Qn and Qn plus 1 as my input values and S and R as my output. Means I am going to observe my circuit from outside to inside. So these are two variables. So 0 0 can be the combination 0 1 1 0 1 1 combination. Now observe clearly Qn and Qn plus 1 is 0 0. Qn and Qn plus 1 are 0 0 at this particular case. This is 0 0 at this particular case. 0 0 0 0. Now what are my values of S and R for these two things? S and R is 0 0 and here it is 0 1. So R is changing from 0 to 1. So S is 0, R is don't care. So that is what the thing. Next for 0 1 combination. Where is 0 1 combination? Here it is 0 1. No other combination. So 0 1 the value is 1 0. So I am writing 1 0 here. Next 1 0 combination. 1 0 I am having 1 0 at this particular case. This particular case my input values are 0 1. So 0 and 1. For 1 1 combination, so I have 1 1 here, I have 1 1 here. So here 0 0 value and 1 0 means S is changing from 0 to 1. So S is don't care, this is 0. So this is the excitation table for my SR flip-flop. Now whether I got the correct values or not, we can check by the S series, that is You observe clearly. 0, 1, 0, don't care, should be in reverse order. Should be in reverse order. So the value which is came here down should be the first value, next to 0, next to 1, next to 0. So if this is the order that you have received, then you have done your table properly. Now I need to get my Boolean expression for my SR flip-flop. Now these are my given values, right? These are my given values. I need to write the Boolean expression for my SR flip-flop. So I am drawing a K-map. So this is my next state expression Qn plus 1, and my inputs are SR Qn. So Qn can be either 0 or 1. SR can be either 0, 0, 0, 1, 1, 1, 1, 0. Okay, the K-map I have drawn. Let's define the values with a different color. Now you got 0, 0, 1 as 1. 0, 0, 1 as 1. So 0, 0, 1 is 1. Next 1, 0, 0 is 1. 1, 0, 0. So 1, 0, 0 is 1. Next 1, 0, 1. 1, 0, 1, 0. 1 is 1. Next don't care sir, 1, 1, 0 and 1, 1, 1. 1, 1, 0 is don't care. 1, 1, 0 is a don't care. Okay. We have marked all our required things from the table. Let's group them. Now this can be a group as a quad, and this particular two ones can be a group here. Now let's write expression for my next state, that is Qn plus 1 is equal to Qn plus 1 is equal to, for this particular quad, left side the value common is S and the top is changing, so nothing I am going to consider, and for this particular pair left side value common thing is R bar, and on down it is Qn. So my Boolean expression for my SR flip-flop is Qn plus 1 is equal to S plus R bar Qn is my expression, Boolean expression for my SR flip-flop. Okay, this is what regarding the SR flip-flop. Let's get into one more flip-flop. One more flip-flop, that is D flip-flop. Let's talk about D flip-flop now. D flip-flop is the same diagram. The same diagram I am drawing. You just see, observe the changes, what happened to the diagram. We are having a cross coupled connection here, Q, Q bar, and this is D input. I am joining this one. This is S, this is R. So what I am doing, I am just combining S, these two terminals with the input to D. Now here D stands for data or delay. Now I am combining these two also by providing a clock. So this is a circuit diagram which is going to tell me about the D flip-flop working nature. Now let us write the transition table. Transition table for my D flip-flop. Now what is my input? I am having only one input here, D as my input and output function. If D is 0, output is also 0. If D is 1, my output is also 1. Why? Because if D is 0, S is 0 and R is 0. For 0, 0, the output is no change, means whatever the value is there, that one only. So no change is getting appeared, right? Now for 1, 1, the one set state is only replaced here, set state. Sorry, here a not gate appears here. That is for 0 state, S value will be 0, R value will be 1. So 0, 1 combination is giving me a reset operation. Sorry, I am removing this thing. I am removing this thing also. I will add one NOT gate here. This is a NOT gate. Now this is 0 and 1, which is giving me a value called as reset. For 1, it is 1 and 0, that is set state. So reset state and set state as my transition tables. Next one, characteristic table. So characteristic table can be written as characteristic table. So it is going to have D, Qn and Qn plus 1 as my next state. So two values. So for 0, present state can be either 0. For 0, present state can be 1. For 1, present state can be 0. For 1, present state can be 1 also. So I got two things. So for 0, it is reset, means it is always 0. For 0 input, irrespective of my present state, my output is always 0. Next, for 1, it is a set, means irrespective of my present state, my output is always 1 here, right? Now I have got my characteristic table. Let's get my excitation table also. Excitation table, that is, we need to observe from output to input. So my outputs are Qn plus 1 and my output is D. So 0 0 0 1 1 0 1 1. So for 0 0 combination, so 0 0 combination D value is 0. For 0 1 combination my input value is 1. For 1 0 combination my D value is 0. For 1 1 my D value is 1. So this is your excitation table for my D flip flop. Now let us draw the we need to get the Boolean expression for my D flip flop also. Let us draw a K-map for this particular thing. Using characteristic table only we are going to draw the K-map. D is my input, Qn plus 1 is my output, and D and Qn is my output values. Qn can take either 0 or 1, D can take either 0 or 1. So one value is at 1 0 and 1 1. 1 0 is this one, 1 1 is this one, right? So I can take a pair like this, right? So my output expression, Boolean expression for D flip flop Qn is equal to, left side it is D bar Qn. So my left side value which is common is D, and top it is changing. So no, I am not going to consider anything. So my Boolean expression for my D flip flop is Qn plus 1 is equal to D. We have done only a small change for D flip flop, that is, from SR flip flop we connected S and R, set value and reset value. S stands for set, R stands for reset. We just connected them using a inverter here. With this we have converted our SR flip flop to D flip flop. Now for every flip flop you need to mention transition table, characteristic table, excitation table, and we need to derive the Boolean expression for that particular flip flops. Thank you one and all. We will meet in the next session.